The title is The Long Road to a Universal Influenza Virus Vaccine. But I want to start out reminding us that vaccines are really wonderful. They work very, very, very well. But that the road sometimes to an effective vaccination that everyone takes it is a long one. And I want to start out with a slide you have probably seen. We all have learned in high school that Edward Jenner, 1796, vaccinated Jim Phipps with a cowpox vaccine. It's quite interesting. This was a 9-year-old living on the estate of Edward Jenner. There was no patient consent. The ethical standards were quite different, but it worked. However, it took 181 years until we had the last smallpox case in Somalia, and only 3 years later was the WHO able to declare the world free of smallpox. So it was a 200-year effort, really. It was not easy. As a matter of fact, like 4 or 6 years after Edward Jenner did the experiment of vaccinating this 9-year-old kid, a 9-year-old boy, there were already people who said, this doesn't work, this is terrible. And so this is a cartoon from 1802. And what you can see is the physician is vaccinating the patient, but then you can see here the other patients, there's something growing which looks like a calf. So it was cowpox. So you can see all the things here which are very unnatural and show that people were not very happy about this vaccination. In fact, this is now a pamphlet from 1891, 100 years later, exposing the evils of vaccination. Okay, so you can see it took a very, very long time, and people were not really accepting that this was a good thing to do. Although, and you just look at the numbers here. This is from Global Health Council. In the 20th century alone, the estimates are that we had more than 300 million deaths. Now, this is really from 1900 to 1920, okay? And the numbers of all the horrible wars we had, I think it's very comparable that smallpox was a real curse. And I think we should be thankful that we had Edward Jenner and that vaccination finally was done, and we have eradicated this disease. I also want to mention that along the theme that vaccination is really good for us is poliovirus vaccination. Most of you have probably not seen this, but this is a hospital ward with iron lungs. And the poor children, infants, who had paralytic poliomyelitis, when the chest muscles were paralyzed, were put into these mechanic ventilators. And you can see here there are dozens of those iron lungs. But what very few people know is that few of those patients ever left the iron lung. And that's something which is really terrible, I believe, and drives the point home that this was very, very bad. But we have basically eradicated poliomyelitis, poliovirus infections, except for some very awkward situations, and we can talk about this. And the third example of vaccines are good for you is the measles vaccine. And that is sort of here, it shows it in a different way. Those are here the 50 states in the country. And then here we talk about 1960 when the vaccine was introduced. And the colors here show how many cases of measles were in Alaska, Wyoming, etc. And then after the introduction, basically measles was wiped out. And you all know that the American Indians were wiped out not by Christopher Columbus shooting them, but really by the diseases, namely measles, smallpox, etc. And how good the vaccine works, I think, can be seen here very easily. So now let's come back to influenza, and we have seen this slide in its variation. Dr. Schenk showed it. In this case here, I just show it in terms of life expectancy, and here we have 1920 up to 1900, up to 2000. And then we have this increase we had 47 years in 1900. And this is for both sexes, male and female. And a baby girl born in 2019 has a life expectancy of about 85 something, I think. But we have, the reason we all show this is we have this, in this case, a dip of 11 years in life expectancy. And this was the 1918 pandemic. Now, coming back to vaccines, there was a bacterium which was discovered in 1892, they called it Bacillus influenzae, and this was thought to be the causative agent of the 1918 pandemic. We had no idea that this was a virus, but there were companies, and in this case, this is Wellcome, the famous company, used this bacterium here to make a vaccine against the 1918 virus, 1918 influenza virus pandemic. Obviously, this was Wellcome here. Actually, it's quite interesting. The successor of Wellcome is GlaxoSmithKline, which is still selling influenza virus vaccines, but the right ones. Yeah? And so this was, I think, a quite interesting historical fact that we had no idea what this agent was in 1918, but we are really people tried to make a vaccine even at that time. Now, we have heard about the influenza virus vaccines, and I want to say right away they are underappreciated. They are not perfect, and I think there's a better mousetrap we can develop in terms of making a vaccine as good as that against smallpox, against measles, against poliomyelitis. But we have right now a vaccine which has FDA-approved vaccines in this country are about involve 3 different platforms. The first one is inactivated, that is, the virus is being grown up, purified, and then is injected, and our immune system makes an immune response against this inactivated virus. So it's not inactive, okay, that's very important. It's just that the virus has been killed by formaldehyde, as Dr. Schenk has mentioned. There's a second platform where there is a virus which has been changed to be very weakened and to only grow in the upper respiratory tract, and that is very good for children, and this is the life-attenuated platform. And then very recently we have a recombinant form which is not relying on any influenza virus, but rather a protein which is actually made by recombinant DNA technology. So there's no virus involved. So those are the 3 platforms which we have. And I think I was very happy to see that many hands up of people who had already gotten the vaccine. Just do it. It's a good idea, really. Get vaccinated. And the problem, however, is that we have a vaccine which really has to be given every year, and it is unique in terms of vaccine. Smallpox once a lifetime, measles once a lifetime, more or less, mumps, rubella, etc. And the reason for that is, and we will talk more about it, is because we have this genetic change. In fact, the vaccines is good. It is actually better than its reputation. If you get vaccinated, it's likely that if you get the flu, it is milder than if you would not have been vaccinated. Now, what are the problems very fast with respect to influenza virus vaccines? We heard already they are not perfect, and this is a CDC data where we just look here at the y-axis. We have here some seasons where it's only 10% effective. It never goes above 60% really, and so that's one of the things which is unfortunate. We have, when we talk about the viruses replicating, we have seen some of this today already. I just show here what's happening from 2000 to 2020. In 2019, we have 4 different influenza viruses circulating. We have 2 influenza A viruses and 2 influenza B viruses, and that shows these branches here, and I changed the color, indicating that from year to year, the virus changes. So if we have here a vaccine with these strains here, they are certainly not good for 2 years hence, etc., because the virus is actually changing. So that's something very important. And this just shows for the vaccine and I saw basically everyone saying yes. We got these 4, including me, I take it too, believe me. We have these 4 components here, where we have 2 influenza A viruses and 2 influenza B virus components. And this is A, in Brisbane is where it was found, and then the year of isolation. The color green means it had to be changed from last year. So this is not good enough anymore. It was decided in February that the formulation would be changed. And that's already another problem for the vaccine manufacturers, that some years 2 has to be changed, 3, sometimes all 4. And that's a nightmare and makes it very, very difficult. So we would like to have, for a universal vaccine, something which is given once a lifetime and protects us all against all different influenza virus strains. Another problem is this here is weak again. This is the amount of influenza. And you can see here sometimes we have influenza week 42, 48. Sometimes it's later. Sometimes it's a lot of flu. The blue curve here, some years it's less. The green one was 2011, 2012. That was a very harmless influenza season. So this is another problem, the timing and also whether it's a bad year or not. And this is really, I don't think it's predictable. What we have here then is in 2009, the blue curve shows when the vaccine was actually shipped out by the manufacturers. And the red curve shows when we had most of the influenza activities. And that's very clear here. So shipping out of the vaccine is not yet in the patient. It is being distributed to Walmart, to the other pharmacies, CVS, and pediatric offices, etc., physicians. So really, the curve is really another 2 or 3 weeks to the right here. So this was too late and really didn't do it. Now, the question then also, and we heard about this, is the other threat is that we have these H7N9, we H10 viruses, H6 viruses, and they pop up here. Fortunately, they are only in China so far, and there is no human-to-human transmission yet. It's only chicken to humans. So this is all in the back of our mind, and the question is then, how can we do better? And flu already, Dr. Schenk made a point in terms of the numbers. So these are real numbers despite the vaccines, despite the antiviral. And we have here the virus. Now this is flu. Influenza is not, it's not a divine visitation upon us sinners, but it's really caused by something, and that is a virus shown here, and we have heard about the hemagglutinin and here the spikes on the outside. So you have to think of this electron micrograph is a very small particle. So if we would have a cell in relation to this blown up enlarged virus, we would have probably 20 of these holes here stacked one above the other. And you have to think about one virus infects a cell, and within 8 hours, 9 hours, we have 100,000 new virus particles. So you can see this is not the best for our for a healthy lung, a healthy respiratory tract. So this is really something which is the virus which is causing the disease, and when we get infected or get a vaccine, then we make an immune response mostly against the hemagglutinin and the neuraminidase on the outside here. So that's what the immune system sees, and we designed a approach, a way of actually redirecting the immune system, not towards the highly immunogenic outside of the spikes here, but rather to, and so you have to think of the spike as sort of a mushroom with a head and then a stalk. And it turns out that the stalk is much more conserved than the very tip of the hemagglutinin spike. So our approach is, and our approach, it means we are 3 independent laboratories at Mount Sinai, Florian Kramer, Garcias Austria, and myself. And we designed new vaccine constructs which can then be given with different platforms, either a recombinant platform, a live attenuated, or an inactivated, not inactive influenza virus vaccine. And what we have done is, so we have here this virus particle, we have on the outside these spikes, and as I said, the very tip of the hemagglutinin is the most immunogenic portion of the hemagglutinin of the virus, and we have sort of basically from an immunological standpoint of view, we have silenced this highly immunogenic tip. And we have used here exotic hemagglutinin tips from viruses which we as humans have not seen yet. And these constructs here are referred to as chimeric because they have an irrelevant head here and a stalk. We use here a chimeric H8, which is this number of subtypes. /1 means the stalk is from a influenza virus from 2019 or 2018, what we had at the time. And so we have two, and then there's a neuraminidase, which is a second minor protein. But again, we hope that our approach of removing this immunodominant head of the hemagglutinin, that the immune system will then direct itself towards the stalk as well as the neuraminidase. And we have two different viruses, so we envision that we will vaccinate with first a chimeric H8/1, then followed by a chimeric H5/1, and that everything is the same in these viruses. The stalks and the neuraminidase and the internal proteins, everything is fine, but they have these, like a stealth bomber that the immune system doesn't know, the radar doesn't see the head of the influenza virus vaccine. And we hope that such an approach is actually working. We have been able to use this successfully I don't show the data, in mice, in ferrets, in guinea pigs. So it works beautifully in mice, but remember, mice are not men, ferrets are not humans. So the ultimate test for that, the ultimate animal test is unfortunately us. And I'm happy to say we are in human trials, and there are phase 1, phase 2, phase 3 trials. This one here is funded by the Bill and Melinda Gates Foundation. And so there are sort of arms in a vaccine trial. So we have to really go through this phase 1, phase 2, phase 3. And so we have here these different arms. And let me just explain here. We have this chimeric H8, you remember this from the last slide, and then /1, the stalk, the conserved stalk is from the 2017, 2018 time, and then a neuraminidase, and then this is primed, and then a second boost, and there are different trials now to look whether 3 months, 6 months, whatever is best, and is followed by the chimeric H5/1N1, and there is an inactivated form here with an adjuvant. In this case here, we have a live followed by the inactivated without the adjuvant. These people have to be, so the trials, because a live virus is being used, they have to be quarantined in a hospital or in a hotel. They can't leave, and they have to be checked whether there's any virus, etc. And so there's a placebo group, and then there's another arm here where both the original priming contains an adjuvant, and adjuvant is a way of making the vaccine more immunogenic, higher protecting, but one cannot give an adjuvant every year. In this case, we are proposing that this would be given once a lifetime or once every 20 years, and the FDA is actually okay with that approach. So we hope that our chimeric construct plus an adjuvant, and this is an adjuvant from GlaxoSmithKline, but I don't think this is important what that adjuvant is, but I think we have to have something to make it more immunogenic to really last for a longer period of time, because a universal influenza virus vaccine for 1 year only ain't universal. It may protect, but if it is not long enough lasting, then we are not helped. So our approach would be to have a long-lasting protective influenza virus vaccine which would be against all future strains. So that's our hope, and I'm pretty sure we should get there, but again, nothing is easy, as you know. So let me sort of summarize. We have vaccination with these chimeric constructs, and we were able to protect our mice, and the mice for a year and a half, but that's again, mice are not men, from heterosubtypic influenza virus challenge. We can do this every day. We can also do this in ferrets. And most importantly, we are now in terms of human trials. But we should also understand that this is phase 1, phase 2, phase 3, and we need 3 components. We need 2 A components and a B component. So these stalks are in these different hemagglutinin groups. We need 2 stalks for A viruses and 1 only, I believe, for flu B. And let me sort of close here with a statement by Bill Gates. The young people always like movies, but we'll see. And
why don't you describe for me,
this is
as
Bill Gates,
vividly as you can, what it is you're working on?
Maybe I'll stop here. So you see, Bill Gates is also interested in it, and we hope that he continues funding us. And and I think I think from an outsider, he is quite impressed what's going on, and I think he understands what vaccines are doing. I mean, his effort to try to eradicate polio virus is absolutely fantastic, and let's leave it at that.
Okay, let's have one question for Peter before we invite the whole group back up.
Excuse me, Erwin Shapiro, Cambridge, Mass. You mentioned, of course, that mice aren't humans. We all agree on that. But what I missed was, how effective was it on mice and for how long? And how did you measure it?
Okay, it worked perfectly well in mice, okay?
I mean, 100%?
Yes, I mean, okay, what we have to do is we have to really use the right amount, we have to use an adjuvant, and we have to have the right distance here. But yes, the answer is it works perfectly well in mice, even in old mice of 1.5 years of age, which is like, I don't know, 70 years in humans, okay? So yes, the answer is it works very, very well in animals. But there are many people here who have worked on cancer, and many mice have been cured of cancer, but it ain't humans, okay?
Okay, thank you, Peter.